All right, so being from a college and having a more teaching perspective, though I do research, I'm going to take more of an educational slant. I mean, if we want people to use these various analysis tools in a appropriate way, we want to make sure that as novices enter the field, they have avenues for getting educated about how different methods work, how well they may work on different types of data, and get a sense of the appropriate use of these various tools. So this is work that some of my wonderful students have helped me with. Two groups of summer students who are just absolutely wonderful in their enthusiasm and just diving into all this, and just really from scratch learning all kinds of stuff about the circadian rhythms and how to develop Shiny apps and about all these analysis methods. So they've been just really exciting to work with. So I think that's also just sort of a nice part of the educational slant, is that you can educate people by having them help you, and then the tools they produce can go on to help others. So, why involve undergraduates? There are drawbacks in that they have sort of minimal background. It is very time consuming, but part of our mission at the college is we really want to expose students to research. We have a lot of students who come in who want to go into the medical field and don't realize there are other possibilities, such as a more primary research career, rather than becoming a physician. And data science is also very hot now, so providing more opportunities for them to get training in data visualization and experience with programming, different kinds of analysis, is pretty important for students right now, so that they can pursue the career tracks of their choice. So I just wanted to show off a couple of the apps they made, and these are available online, and I'm happy to share any code of any analyses I've done, whether it's these Shiny apps or from other papers. I agree with the open source idea that we want code to be accessible and usable and freely shared so people can continue building on it. So I'm going to switch so we can get more of a live version of this app. Let me see if I can switch over to that. All right, so hopefully you're seeing the CIRCADA-E app here now. And so the idea behind this is it's a curated data set produced in Mary Harrington's lab. And this was an app produced in collaboration between my students and several of her students, who provided feedback on the interface and the kind of analyses they wanted. And sorry, my cat's interfering. There are several factors. You can choose the age of the mouse, the light dark cycle length was under 20 or 24 hours, the diet, normal or high fat. And then you have a whole bunch of different types of data. You have lumicycle data from multiple tissues, the locomotor activity record, which is what I'm showing here from one of the mice, and body temperature. And so through this curated data set, students can explore how different methods work. There's a number of educational features that my students built in. For example, to learn about the discrete wavelet transform, there's a little feature here where you can step through the different levels of each processing stage of the discrete wavelet transform and see as the high frequency noise is extracted in red there from the blue signal, how it's progressively smoothed as that part's removed until you get to the last layer, which is a very smooth circadian component. And so this can allow users to learn a little bit more about it, try it out on different types of data, and decide, is this working the way I want? Is this giving me the kind of analysis that seems useful for this type of data? So they can actually try it out on these multiple types of data. There are also little pop-ups, so you can ask, how does this work? What is this about? I think visualizations are important. Loam-Scargill is pretty popular, and it will report periods to a bunch of decimals. But what people may not realize if they don't actually see what the graph looks like is that the periods are actually quite discretized, and it's not a high resolution method unless you have many, many cycles, which even here, when we have quite a few cycles, it's still not that high resolution. So to kind of educate students in what are the limitations of these methods, as well as the things that they can provide to you. And show one other little educational one for like autocorrelation. They made a little movie so that you can sort of see it in action, that the idea of autocorrelation is to take a copy of the time signal and gradually shift it until it best matches itself. And that can give us different period estimates and a sense of how consistent the rhythmicity is, a rhythmicity index reflecting the strength of that rhythm. So then the other one they made, so this, oh, and I should point out another use that's been made of this app is in circadian clock courses for undergraduates. It can be hard to find a good data set to let students work on a project. And so another purpose of this was to provide this curated data set. And you can have students form a hypothesis based on these different factors about what they think, how they might affect the rhythms of the mice, and then carry out an analysis. That there's all these built-in tools, a nice clean data set that's all ready for them to work with, that's pretty rich in the different types of data that are provided. And Mary Harrington, who's been my collaborator in all these projects, has had great success with that in her circadian clock course, of being able to use this to provide students with a curated data set coupled with an analysis method. So then just to take a quick look at its sort of complement here. Hopefully you're seeing CIRCADA-S now. The idea of this is it produces synthetic time series and allows for example, a power analysis. You may say, okay, I know these characteristics of my data. I'm going to be able to collect this many days at this sampling rate. I have this kind of noise and this kind of trend. For these different methods, what do you expect to be, for example, the number of mice you might need to use in the study in order to detect a given difference. So this idea is that you can produce large sets of synthetic time series with desired characteristics and use that to test out the different methods, see which might work best on your particular type of data, and also get a sense of how many data series you may need in order to detect some kind of difference that you're interested in. So all right, so then let me just, I always like to show this graph sort of in conjunction with this, just to highlight the difference between how much improvement do we expect in estimates if you can increase the number of cycles versus the sampling rate. So I think people often think to increase resolution in period and phase estimates, that the natural thing to do is to increase the sampling rate, because that kind of makes sense in a certain way. But actually what you really need is more cycles. So on the left, you can see that for having a time series that's either 3 or 4 days in length, in a representative sample shown of this kind of time series, how many samples do you need to get a certain power? So the usual cutoffs, you want 80% statistical power, so you have an 80% chance of detecting. In this case, we're looking for a half-hour difference in period. And if you have 3 days of data, you're going to need to use probably around 29 mice, according to this estimate. Whereas if you could just find a way to add 1 more day, you can bring that down to more like 21. So that's a considerable difference of sort of 20 versus 30. And this kind of tool can let you sort of explore those, how based on different parameters of, how many days versus sampling rate, what are you going to need in order to carry out your study. On the right is just, again, emphasizing this sort of diminishing return of increasing sampling rate that you can see for a fixed number of days. As you greatly decrease the sampling rate, you just really don't get that much difference in your error. That you get an initial difference, and maybe 2 hours is a little too coarse, but dropping down to 1, you don't really see much difference in doing anything at a smaller sampling interval. That really where you get the biggest gains is if you can manage to add another cycle somehow to your data, that's where you're going to get the biggest gain. Right, and then we have CIRCADA-I is under production right now. So the drawback between the previous apps is that people can't upload their own data to explore. So we're developing an app that will allow users to upload their own data, and we're trying to make it as robust as possible by having them make choices about how do you want your outliers treated? How do you want your missing data treated? Do you want your data binned in any way? Do you want to detrend it in any way? And doing lots of visualizations to help them with that sort of pre-processing stage, getting their data ready to go then into these different analysis methods. And then just for fun at the end here, I just wanted to show a visualization app. So this is just for fun. It shows instead of actigraphy data, this is Gmail, Twitter, phone app. You can do other kind of generic things. And just to really highlight for people what's different about different ways of presenting data. And choice of color, choice of layout. One of my favorites is spiral, since time is continuous. Gives you a sense, and the idea was comparing pre-COVID to post-COVID data from people, that we can see this person in particular in post-COVID has a lot of evening Gmail that they didn't do so much pre-COVID. And then you can see the difference. It's showing up in blue here, just sort of to highlight what they are. So I will stop there. And
thank you very much, Tanya, for that lovely talk. Wow, to actually have apps developed with undergraduates that could be used by undergraduates, that's pretty amazing. So now I open the floor for questions to the audience. If you have any questions, could you type in the Q&A? Well, while the audience questions are coming in, I am going to ask you one question. So is this app something that researchers can use as well? This is not just a great teaching tool, but it seems to go beyond that. So could we use it in our labs as well?
So the existing apps are really purely educational, but once we get the interactive app up and running, and we really want to do sufficient validation to make sure that it's completely robust, then that will be something that researchers can be uploading all kinds of their own data to and actively using.
That's absolutely fantastic. Let me see if there are any questions. Well, not yet. And I'm going to ask you one question before I move on to the next speaker. So one of the things that I like to think about a lot, and this might actually touch on something that Olivia said. So a lot of apps come out, a lot of wearables come out. I think it's a fad of the day. People use it and then it just fades away. Do you think that this is something that could be used on a broader scale to sort of educate the public on things like sleep hygiene and the importance of circadian rhythms? Because this seems to be a big movement with sleep researchers, is also to get the public to understand that sleep is very important for health. Circadian rhythms are important for health.
Yeah, no, that's a great question. And that sounds like a great next project for the next batch of summer students. Is to create an app instead of aiming at students entering the circadian field, to have it more widely available to the public and have that educational aspect into it, not focused on so much the analysis, but visualization and what does this mean to you, in your personal life, and how can you be changing things? That's a great suggestion.
Thank you. Thank you very much, Tanya, for this lovely talk. And I'm sure we'll have a lot more of an intense discussion in the panel session.